Why do you have two homeworks? Okay. So you've just submitted homework number 5, and homework number 6 will be due, well, I don't mention it here, it's due a week from today. Let's just double check on the schedule to make sure. I intended to put that on there, but it's under syllabus. We'll get to other questions in a second. So the next homework 6, yeah, it's due a week from today on Sunday, the 18th of October. As you can see, the midterm is going to be on October 20th, and that will be in class. I'm still thinking through when to have the location of the midterm, and so guys, class starts at 12 o'clock, and I'm not trying to be annoying, but if you come in late, it's very disruptive. So please be here at 12 o'clock, all right? So back to these announcements. The homework is due a week from today. Homework 6 is due a week from today. And we're going to be talking about coagulation and flocculation today. So after this lecture, you can get an early start on that assignment, just so that if you have any questions that pop up along the way, it'll be easy to get that done early. One thing I wanted to point out here on our course website for iLearn, occasionally I'm going to have extra things for you that I may not hand out in class. So if you go into lecture notes, there's a folder here that's called Other Items. And what you'll see is that occasionally, not very often, but occasionally, if we had to rush through an in-class exercise and I feel like you didn't get a chance to maybe do all the calculations or copy down the solution from the screen, sometimes I'll post those solutions in that folder. So I know that some of you have already found that, but I just wanted to point out that if you're not sure where that's being posted, it's under Lecture Notes, Other Items. Yes? Okay. Well, yeah, let me make a note, and I'll double check on that. All right. So we're going to be talking about coagulation, flocculation today. Before we do that, though, we didn't get to look at this slide during our last lecture, and I wanted to spend just a little bit of time telling you about water softening on a house-by-house basis. Softening, if you do it for the whole municipality, usually the approach is to have chemical addition. You'll add lime to remove the hardness, and sometimes if you have a lot of non-carbonate hardness, then you have to add soda as well. Will you put away your phone? Thank you. So if you live in a town and they're not softening the water for you and you want your own house water to be soft, you can have maybe in your basement or in a utility room something called a water softener or an ion exchange resin. And the way this works is it exchanges sodium in place of calcium and magnesium. What you'll remember is the definition of hardness is any ion that's positively charged and has a valence of 2 or more. And so the most common ions that add to hardness are magnesium and calcium. Iron and manganese also add to hardness, but usually the concentration of iron and manganese is relatively low. And so on a quantitative basis, it doesn't add that much hardness. What this can do is the water will flow through it. The hard water flows through, and inside this resin, there's a lot of sodium. So let me here on the whiteboard do a drawing just to show that initially this resin has a bunch of sodium, which is +1. And so when a calcium comes through here, when a calcium 2 is going through the resin, it will get stuck. So it stays. And then what goes out is 2 sodiums to replace the calcium that stays. The overall charge balance has to be the same, but by keeping the calcium in the filter and discharging sodium, the advantage is that the water is soft now. There's no longer the hardness isn't contributing. All right, so it's a means of softening the water. And the disadvantage, though, is that sodium can cause high blood pressure. And so if it was really, really hard water and you're replacing all of that hardness with sodium, then it can lead to hypertension. And so usually when people have soft water in their house, it's just maybe for bathing only. And then they'd leave the hard water going to the faucet for drinking. Or maybe they'd have a separate drinking water source. So this is called ion exchange. And it's one other option besides chemical addition for softening. So today we're talking about the process of coagulation and flocculation. And coagulation flocculation is a process that's intimately linked because what we need to do is remove particles that are stabilized. And stabilized particles is bad in drinking water treatment because it means that the colloids can't be removed and the water stays turbid. So just to summarize, this is our groundwater process where we're starting with water from wells, and we want to have in the end clean, pure water that can go directly into the distribution system, like towards people's houses. So what we're talking about today is one of the first reactions that happens in rapid mix and the reaction basin. In groundwater, usually there's not very much turbidity. Typically, groundwater has a pretty good clarity, except for sometimes there's natural organic matter or there can be a colored tint to groundwater that coagulation and flocculation is able to remove. Usually, surface water is more significant for coagulation and flocculation because surface water has more turbidity. If you think about how rivers can look brown and silty because of the clay particles that are in it, coagulation, flocculation, sedimentation, and the other steps afterwards are all meant to remove particles that otherwise can cause human health problems. So there's a couple of animations that I want to show you. First one is coagulation, and what we're going to see in this is the chemical reaction sort of visualized. The chemical reaction is having the effect of destabilizing the particles. And so the clay particles are what we want to change, and alum is a coagulant. So watch what happens as the alum is added. The change that you're supposed to see is that the particles aren't moving around as much as they used to, and they're starting to get bigger together. So let me just step you through this one by one. These little red dots are clay particles, and that's what makes the water seem kind of murky. Now, the clay itself isn't harmful to humans. You can swallow clay, and as long as you're not swallowing too much of it, you're not going to have any problem. It's just a mineral. But what's the problem is that bacteria can hide inside of the clay. And so it's not the clay that's going to make you sick, but it's the viruses, bacteria, protozoa, microbes can stick inside the clay. And so we need to, as much as possible, get any impurities out of the water. So in the beginning of the video, what it's showing is that these particles, they won't stick together. When they start to get close, they repel each other, kind of like magnets. If you've ever played with magnets before, you know that when you turn the magnet sideways and you have both of the negative sides together, they just kind of bounce apart naturally. And that's what happens. These little particles have a negative charge on the outside, and so when we start to stir them, they're bouncing all over the place, but they won't stick. So we add the chemical, and suddenly they calm down a little bit. They're not having the same repulsive forces that they initially were. Now they're stable. And so Actually, the coagulation process has tried to make it so that these particles aren't moving around as much, and so that we can get them close together and so that they'll stick. All right? Coagulation happens in chemical addition, and it's a very quick process because it's a chemical reaction that can last less than a second, and so in rapid mix, the mixing energy is very high in that stage. And the tank volume is relatively small. There's not a big tank there because you don't have to be stirring it for too long. The water just passes through quickly after the chemicals are injected. Flocculation, on the other hand, is a more lengthy process, and the mixing energy is lower during flocculation. So the particles come in, and they've been neutralized already from coagulation. And you can see that the particles are progressively growing larger as you go from tank to tank. In the first chamber, the mixing is higher energy. And there's a couple ways to achieve that. You can either stir it more quickly, or you can have more paddles. In the second chamber, the way that you want to have lower mixing energy than in the first, and so you'd stir it slower, or you'd have maybe only one paddle instead of two, and so on. Now, this is not to scale. By the time the water gets to the edge of the reactor, the particles aren't actually that large. It's just kind of a conceptual diagram to show that the flocks are growing larger in this process. All right, so during the flocculation stage, it's taken neutralized clay particles. And what do you think it means by neutralized? It's charge, exactly. A clay particle, to begin with, is surrounded by negative charge. In coagulation, we're adding a chemical that's going to neutralize that charge. Because if we have two clay particles that are both negative, we can't get them to stick together. It's like two magnets. They won't stick. So the coagulant neutralizes the charge so that they can stick. And now in flocculation, just gentle mixing. And the purpose for the gentle mixing is to have collisions. You want those particles to collide with each other so that the flocks will grow. And now in the third step, in sedimentation, we can see that the large clay particles, we're going to put a big quiet tank where the large particles can settle to the bottom. You can see a sludge is forming at the bottom. So when it gets too deep, you begin to pump the sludge out the bottom. All right? Does it remove all of the particles? No? Yes? Of settling? No. There's typically only one settling chamber. And so you're probably wondering, well, what about the rest of these particles, right? Oh, flocculation. Usually in flocculation, this is just a conceptual diagram showing that, you know, one chamber here. Usually there's three chambers. That's kind of the typical thing, but you'd only have it going through one time. So it would make one pass through a three-chamber area. Yeah. All right. So here, you notice that there was still a little bit of particles left even after sedimentation. It removed most of it, but then the rest of those small particles will get stuck in the sand. We'll talk more about filtration later. But I hope those animations give you kind of like a conceptual idea of what's happening and why we're adding those chemicals. Are there other questions before we keep moving? Yeah.
There was still charge in clay that's going to the flocculation.
Yeah.
How do you make sure to get
You have to, that's a really good question. You have to make sure to add the right amount of coagulant. And we're going to talk about dose today. So his question was, what if there's still clay particles that aren't destable, that haven't been neutralized? You know, if they haven't been neutralized, then they're not going to stick together, and your treatment may be unsuccessful. So The what if is you just got to get it right the first time. You have to put in the correct dose. And so at a real water treatment plant, they're going to be taking measurements every day to see how the turbidity is changing. And how much coagulant they add varies depending on, what's the quality of the water coming in today. And even a very large river. I live next to a huge river in the United States called the Ohio River. And you can just look at it from day to day. The color of the river is changing based on how much rain there's been. If it's a very heavy, rainy time, then the water becomes more cloudy and more murky because the soil is getting in during a flash flood. There's a lot of erosion in the soil. Was there another question? The problem is that the coagulation reaction with the alum, it's very quick. And so you're saying, can't you let it to spread out everywhere, right? That's what you want. You want it to spread out everywhere. And so to do that, the best way to do it is to inject it in multiple locations inside of the mixing basin. You have the best chance of success. Here's our mixing basin. Let's inject it here and here and there and here, lots of places. It's kind of like with cars, right? In a cylinder, they have multiple fuel injectors per cylinder to try and spread out and make sure that the fuel gets everywhere in the cylinder. So you have the most complete combustion. Here, you have a lot of mixing energy, or you inject it in multiple locations because that reaction is very quick. Here are some images that are showing you the need for coagulation. What we see is clay particles that are turning rivers brown. The water itself is still clear, but it looks brown because of the suspended particles. Here you can see water from a river is coming into the ocean. And where the river enters the ocean, there's turbidity, but then the ocean itself has a higher clarity there. Here's just a series of jars with progressively increasing turbidity. Turbidity is the measure of colloid concentration. Colloid, let me write it here, C-O-L-L-O-I-D. It's just a clay particle. How come we don't have to remove gravel from water? Like we're talking about clay or sand. How come sand and gravel isn't an issue? Why am I, soil is sand, gravel, clay. Why am I talking about clay and do you suppose not sand and gravel? They don't have an outside charge, that's true. Okay. All right, the void ratio of clay is high. Okay, actually we do, you've got a point. We do use sand during the filtration process. The main reason has to do with the size of the particle. If there was any gravel in this river, it would settle to the bottom. It's not going to be floating around. Gravel, it doesn't float in the same way that clay particles are so small, they continue to float. And the same thing is true with sand. Sand will float better than gravel, but still the velocity has to be very high. And once you slow down the water, the sand settles very quickly. So what we are interested in removing from surface water is colloids, which is suspended clay particles, color, and natural organic material like decaying leaves. When in the fall, when the leaves fall off of the trees, it can change the color of the water to a yellowish or a brownish tint. And then there's also pathogens. And usually the pathogens are stuck in or on the surface of particles. So very small particles won't settle on their own. And I've got an animation to show you that. But one of the ways to measure the clarity of water is with something called a Secchi Disk. And this is something where it's lowered down into a lake or a river on a line, and it has a weight on it, like a lead weight, so that it's going straight down. And you measure how deep into the water can it go, and you still distinguish the white from the black. So it's just a visual measurement, and there are some lakes with really high clarity, like in the mountains of Switzerland or in the high mountains in California, where you can put that disc down very, very deep, like maybe 30 or 40 meters, and still see the distinguishing between the white and the black section. So here's a photo of a clear alpine lake where the clarity of the water is very high. Other times, there's a lot of soil in the water that stays suspended, and so that's turbidity. And what keeps them suspended is Brownian motion. Let's take a look at a quick video that illustrates Brownian motion. So imagine that the blue is a clay particle. Why won't the clay particle settle on its own? Why do we have to do something special to get it to settle? It's because the water molecules are moving around just due to their own kinetic energy. Water is always moving around, and they're bumping into the clay particle enough that they keep it suspended. Even if we have turbid water in a tank for 5 years, it will still continue to be turbid looking. The particles, there's a certain size where it's just, the particles are too small to settle on their own, and so we have to do something special to get them settled. So that's something special that we do is by adding the coagulant. The coagulant is a chemical that causes neutralization of the charge on the colloid. The two most commonly added chemicals are alum, which is aluminum sulfate, and ferric chloride. And just another piece of nomenclature. I know I've defined this before, but it's important to know what a flock is. A flock is if we can get these two particles to stick together, then that's a flock. Or hopefully we can get 3 particles, or 4, or 5. Why do you suppose it's better to have a lot of particles stuck together? What's the advantage of that? It settles better. The Brownian motion is trying to keep it suspended. All the water molecule movement can't keep a big particle suspended. The larger it is, like a large piece of sand or a large piece of gravel, the larger it is, the more quickly it settles. So small particles stay suspended. Large flocks will settle more easily. Yes? That's right. Yeah. So the clarity of the water. If you have high turbidity, that means the clarity is low. So here's an illustration that shows our clay particle. Here's a colloid that, because it's small and because it's made out of clay, has a negative charge surrounding it. If you have another clay particle, then there's going to be a repulsive force there, similar to if it was just a pair of magnets that you were playing with. We want these particles to stick together because when they stick, then we can get it to settle. Or, you know, there's still a little bit left over after settling. If they're bigger, then there's a better chance that we can get it to stick in the sand filter. So it's also helpful if we neutralize that charge. It improves our sand filtration performance. So to get it to stick together, we need 2 things. We need collisions, and we need this negative charge to be neutralized. I've said here a sticky surface. Right now you think it's repulsive, but we want them to get to stick together. And so by adding the chemical, here is a representation of the coagulant. If you have a bunch of positively charged ions in solution, then that will make the repulsive force weaker. Here, the repulsive force is strong. 2 negatively charged, they'll never come together. Even if you are causing collisions, even if we are mixing the water and these bump into each other, they never get close enough that they actually stick. Before they can get close and start to stick together, the repulsive force pushes them away. So we have to have both of these, collision and a neutralized surface, to cause the flock to grow. So coagulants is a class of salts that will cause this neutralization of the negative charge. It suppresses the negative charge so that the particles can get closer together. Now here's a graph taken from our text that shows the relationship between the charge and if salt is added versus no salt is added. So you can see initially this upper line here says no salt. And so you can measure how strong is the negative charge as a function of distance, how far you're getting away. And so think of these flocks that are drawn on the board here. It kind of has like a force field going around it. And so that repulsive force is all the way around the colloid. And when you have no salt in the water, that force field is very, very big. But when you start adding a positively charged ion into solution, then the negative charge from the colloid doesn't go as deep into the water. So here you can see by adding just a little bit of salt, suddenly the repulsive charge isn't going very far into the water anymore. And if you add a lot more salt, the more salt you add, then that's neutralizing more of the repulsive charge for the colloid.
So any of the salt is acting as the coagulant?
That's right. And both ferric chloride and alum, those are both salts. Sodium chloride isn't the only salt. There's other constituents that are salts that they dissolve well in, they're inorganic and dissolve well in solution. This next figure is showing something that I want to see if you can tell me the interpretation. One of the things I like to do in exams, I like to give the student a picture and have the student tell me, explain this figure. So let's practice that. What do you think this picture is telling you? All right, what do you mean by that? More details. Okay, that's right. Exactly, yeah. So in the top figure, this is a +1 charge. So it partly depends not only on how much salt you have, but also what kind of salt. And remember, we've talked about polyvalent. So this is divalent. Both of these are divalent. And there's monovalent. For example, monovalent would be Na plus or K plus. So sodium or potassium has a charge of 1. Magnesium, calcium has a charge of 2. Trivalent is aluminum, 3 plus, and iron, 3 plus. What this figure is showing is it's not only how much salt, but it's also whether it's mono, di, or trivalent. And so the higher the valence of your salt, the more effective it is at neutralizing that negative charge. Yes? So he's got a good point. What if now you go like too far? You want to have it neutralized, but if you put in too much, then instead of just being negative repulsion, then it could be positive repulsion. That's what you're saying, right? Like, so here's our clay particle. If we surround it by positives, and here also is you've got too much positives, and now there's a repulsive force again, right? So you only have to get the right amount of coagulant. There is such thing as too much. So coagulant, it's not always that more is better. There's just the perfect amount that neutralizes it, but then if you keep adding more and more, then you go beyond neutralization and you're back into repulsion. Oh, good question. So, like, what if you mess up and you add too much coagulant? No, you can't add more clay because the clay is there naturally in the water. You would have to add maybe more negative charge somehow. Really, what they do is they do something called jar testing to know what's the correct dose. I'll show you a picture in a minute of jar testing, but they do a little experiment in the lab at the water treatment facility before they figure out the dose for that day. Like every day they figure out what's the correct dose based on how much turbidity we have right now. Right.
Based on that, you're not proactive.
That's right. Exactly. Yeah, and in fact, so they do it like a daily jar test, but they're also measuring the turbidity in real time. There's a sensor, it's an optical sensor that looks at the water. It's shining a light through the water, and it's measuring how clear it is. And so the operator, the person who's at the treatment plant, can manually adjust the chemical up or down based on how the turbidity is changing. So let's talk about, like, what's the best coagulant? The ideal coagulant is something that's trivalent. And why do we like trivalent for a coagulant instead of monovalent? What's the advantage?
It has more attraction.
Yeah, you're getting more bang for the buck. It's better at neutralizing the clay. So trivalent is best, non-toxic for obvious reasons. We don't want to be adding like mercury or lead or salts that are harmful to people. And then the other thing is we want it to be insoluble at neutral pH range. That means we're going to add it, but we want to get it back out again. Like, we're using aluminum and iron to get rid of the clay, but we don't want that to stay in the water. So we have to add something that will precipitate eventually and stay out of solution. And both aluminum and iron meet these criteria. So here is the formula for alum. It's aluminum sulfate with water complexed. Iron sulfate or iron chloride is also commonly used. Here are the reactions. For the homework that you've just picked up off the table, it's due a week from today, you need to refer to these reactions. And the reason why is that both alum and iron consume alkalinity. Look at the reaction, and I'll tell you what I mean by that. If you don't have alkalinity, then it's making an acid. Because what the aluminum will bond with is sulfate. I'm sorry, what the aluminum will precipitate into aluminum hydroxide, and then the sulfate that was there will form H2SO4, which is an acid. And the same thing is true with iron chloride. It'll form hydrochloric acid if alkalinity isn't there. So in the homework, you need to look at this, and you need to look for every one alum how much carbonate is removed, like the molar ratio. One alum takes 6 carbonate, or if it's in the case of iron chloride, 1 ferric chloride takes 3 carbonate. So the molar ratio is something you'll have to think about in the homework assignment. Most waters already have alkalinity in them, and so it doesn't change the pH. So hopefully that's the case. When alkalinity is present, then the alkalinity buffers the pH from changing. But still, it consumes alkalinity. The coagulant consumes some of the alkalinity. And also, I'll point out here that a precipitate is formed during coagulation. S in all of these reactions means solid. So that is something that's going to have more mass that will be removed in addition to the clay particles. So by adding these chemicals, the volume of stuff that's getting vacuumed out of the bottom of the reactor, let's go to this one. Do you remember what it was called, what's at the bottom of the sedimentation step? Sludge. Yeah, we called it sludge. And so it showed like a pile of the sludge getting. Let's just look at that video again. Let's watch the sludge accumulation. If we are adding a chemical to cause coagulation, this sludge is partly clay and it's partly alum or iron. So what contributes to the volume of the sludge includes the coagulants themselves. All right, so here we are. Any questions so far? Yes?
When you say solid, can it also be liquid? Like, not solid only?
So you mean in terms of this?
Yeah.
When we add it, it's dissolved. So aluminum sulfate is dissolved, but what we mean by insoluble is that we want to get it out again. So you can add it as a liquid, but it shouldn't stay as a liquid the whole time. Like after it does its work, it should then precipitate, because we want the water not to pick up additional chemicals along the way. So it's just temporarily a liquid, but then it precipitates. Here's a picture showing the jar test. This is how they find out the correct dose. Because if you add too much, that's bad. If you add not enough, that's bad. So they'll take a sample of the water and they'll put a different amount of coagulant in each of these jars, and then they'll stir it the same amount. These are connected to gears, so they get exactly the same amount of stirring energy, so that the only variable is the concentration of coagulant that was added. And so they'll put in a coagulant, stir it for some time, and then stop, let it settle, and then measure the turbidity to find out which one is most clear, and that gives you an idea of the ideal dose. The concentration with the best bridging and charge neutralization, the concentration that gives you the most clarity is what you choose for the full-scale water treatment test. Here's just another example of what a jar test apparatus can look like. In the homework, I give you a table. And it is something that you need to graph, and you pick the correct pH on this graph. In our case, I'm just asking you only to graph the dose. So here is turbidity on the vertical axis, and alum dose is on the horizontal axis. What is the ideal alum dose that should be used? What would you say? How much alum should they add to the water? Yeah, 12. Maybe just a little bit more. I don't know. I think here is 12, and it looks like it gets a little lower. It's hard sometimes to interpret too much when it's connecting the dot and curve fitting. But yeah, 12. 12 is the one that gives you the lowest turbidity. So you'll do the same thing on the assignment. You're going to graph the dose and then check and see what's the turbidity, and from that pick the ideal concentration. And it looks like the best pH for this one was about 6.2. So that's the best pH that you'd want to have during the coagulation phase. If you need to adjust pH, that can be done with lime. And we've talked about lime already through softening. It helps. The settling of particles is better at different pH. Sometimes you can make a flock heavier by adding more clay. And earlier there was a question of, do you add more clay if you do too much coagulant? And you don't add more clay if there's too much coagulant, but you do sometimes add it to make the particles themselves heavier. Like if you have just a little bit of clay, then maybe there's not enough for them to be sticking together. Usually nowadays, instead of adding more clay particles, they're starting to switch to something that's called polymers. They're like proprietary plastics. And here's an illustration that shows what a polymer does. A polymer is like a very small piece of string that will cause the negatively charged colloids to get tangled up in the string. And so when they're tangled up and destabilized, they'll settle a lot better. So it's kind of like a net for coagulation. Here is a special kind of it's a cross-section of a special tank where both coagulation and flocculation happen in one basin. And this is kind of interesting that they've managed to figure out a way. In the center, they're doing the rapid mix, and then the water comes out of the rapid mix chamber, and the water itself is floating up while the particles are settling down. The particle, when it gets to the bottom of the tank, there's a sweeping arm that will push it towards the center, and then it's vacuumed out and the sludge is removed. And so this is just kind of an interesting, more advanced chamber where both rapid mix and flocculation settling is all happening in the same chamber. And the advantage with that is it can save land area. In places where the real estate is very expensive, like think in an urban area where the cost of property is very high, then reducing the footprint of a treatment plant is very important. But the problem with this solids upflow solids contact is that it's not very adaptable to changes in water quality. And so it's typically used for groundwater or for surface waters that are pretty stable. All right. So with the remaining time, what I'd like for you to do is, the in-class exercise doesn't have calculations. It's conceptual. And that's a change from what we normally do. Normally, you know, we're crunching numbers. I'd like you to, in problem 1, just do a drawing to summarize your understanding. Like make a figure that you could explain to someone else what happens during coagulation. And then in part 2, do a short answer explaining why the mixing energy decreases. And what I mean by that is, you remember we saw the video of flocculation? Why is it that we want to have high energy, medium energy, and then low stirring energy? That's the essence of the second question. There's more than one right answer here, because I'm just asking you to explain something in your own words. So my solution is going to be pretty lengthy. It doesn't have to be as lengthy as this, and maybe you have a better drawing. Okay, so what I did to illustrate is like the before and the after. Here, the suspended particles, they're suspended because the water is moving around, and the Brownian motion is keeping those particles suspended. Even if we left it for days, weeks, years, those particles still won't settle. They're just too small. So before, there's a strong repulsive force. And then the after, you can see I've put some plus charges in there. That's the coagulant. So after, they get closer together. Any questions about the idea behind the first one? Oh boy, that's long, right? Why is there progressively less mixing energy added during flocculation? You could write, so the flocks don't break apart. I mean, that's the essence of it. If there was too much energy, then the flocks will break apart. But what I'm saying is, you're trying to encourage the flocks to get bigger. And so you want to have enough mixing so that they collide, because that's how you do get it bigger. If you don't stir it at all, there won't be collisions, and they won't get larger, and so it's like a balancing act. There has to be enough mixing energy to promote collisions, but not too much, because if there's too much, you'll start to shear them apart. Big flocks are delicate, so you have to have progressively less energy. You have to be very gentle with those big flocks, because they're not very rugged. They'll settle, but if we stir a lot, then we'll break them again. All right. So let's just review these announcements here. The next homework assignment is due Sunday, October 18th. And then looking further into the future, here's our schedule. It shows that we have an exam on Tuesday, the 20th of October. So that's 9 days away. Nope, we can't. No. You'll see that the homework is just covering coagulation and flocculation, so it doesn't include sedimentation and filtration. So you have plenty of time to do the homework between now and when it's due. But submitting it after the homework, after the exam, I think would put us too far behind schedule. So it's during class period. So our exam will be held during the class itself. Oh, the material? Oh, okay. It's going to include class 1 through 15. So the exam will cover chapters 1, 2, 5, and 6. Part of 6, not all of 6, because we'll do some of the lectures for chapter 6 after the exam. What's that? Yes, as you ask. You write the exam, and you make it as easy as you want, okay? How about that? All right. All right, have a nice day. I'll see you next time.